All right, folks, welcome back. We are back on record. I'm going to do the paper reading on yet another object detecting algorithm. This is another big milestone in the development of all this object detection and so forth. So recall that in the morning, we went through, what did we do? UNet. Right? We did UNet. Now, before I go into data, I just want to mention a YOLO, which is perhaps widely used for quite some time. I wouldn't get the time to cover it today. Time permitting, I may do it in an extra session. But you can look up its architecture on your own. YOLO is at version V8 as of this moment, or more. V8 is the last I could keep track of it. It is very, very commonly used for object detection and segmentation, but we won't be covering that because I'm trying to cover the conceptual big milestones today. And it is very practically useful. I wish I could cover that too, but we seem to be lacking in time. All right, so coming back to DETR, it says, and the title often with these papers are a giveaway of what the gist of what they're saying. People think of the title of a paper after thinking a lot and writing the paper. Title is the last thing we think of. So it says end-to-end object detection with transformers. What could it possibly mean? You do the entire detection with the transformers, not with something else. Now, this author, Nicolas I hope I don't butcher his name in pronouncing it, Carillon, Nicolas Carillon, he has created a good video, a very short video talking about his paper. It's like, obviously it's meant for researchers to listen to and so on and so forth, but it's a good one. I put it on the course portal as one of the things to listen to, just to get a perspective on how he's thinking. It's very good. Now I'll read this abstract. We present a new method that views object detection as a direct set prediction problem. It predicts a set. Our approach streamlines the detection pipeline. So obviously you can't make out what set. Yeah, we'll come to it. Our approach streamlines the detection pipeline, effectively removing the need for many hand-designed components like a non-maximal suppression procedure or anchor generation that explicitly encode our prior knowledge about the task. This part is a little bit important. What was happening is, and is a history of the thing, image segmentation is a very important task. I mean, people were already, if you look at the time, by the time this thing became V3 updated, you can imagine that this paper was, actually it was published before this date, put on archive before this date, and it came out before this date. What was the thing people were talking about pre-pandemic? The hottest topic seemed to be autonomous car. They seemed to be around the corner. People were even putting down payments for autonomous self-driven cars. How many of you were foolish enough to do that? No. Okay.
How many of you got that Tesla stock?
That's right. Right. So anyway, it just seemed imminent, and obviously in that whole journey.
Tesla gave a full self-driving capability in the car, saying it is going to take care of it anywhere you drive. You don't have to. They just released.
Yeah, they recently, last week released it. Last week they finally released it.
From the guy.
Yeah.
All of it to bring it back to your safety.
Yeah.
Underline.
Right. Okay, so there we go. Sorry for making jokes. All right. Now, what would happen is when you try to do segmentation, and if you look at the existing methods of segmentation at the time, there was a lot of hand hacking. Right? And when people talk about prior knowledge being explicitly encoded, they would know that if it is like this, make it like that. See, what's the problem with methods that encode specific things? There is a statement, and Jan LeCun makes it, and many others make it, that general models that think of the problem in the abstract tend to, in the long run, outperform very specific hacked models. It's a general statement. In fact, you will see later on when we go into JEPA, etc., you'll see more of his thinking come through because we're going to read some of his works. But that's what they're referring to, that at that time, there was a lot of hand hacking going on. The main ingredient of the new framework called a detection transformer or DETR. So now we know where DETR comes from. Right? So are a set-based global laws that forces unique predictions via bipartite matching and a transformer encoder-decoder architecture. Now, if you are not familiar with these terms, you'll feel suitably lost. Right? So let's read it backward and see which of those words in this long sentence make sense. A transformer encoder-decoder architecture. What do we make out of it? Remember that when people use transformers, a transformer is made up of an encoder and decoder, right? The two pillars. People sometimes use only the encoder, sometimes they use the decoder, and sometimes they use both. So we can jubilate in the fact that, okay, at least this part we understood. Encoder, decoder. Now, what comes before that? A global loss that forces unique predictions via a bipartite matching. So, first of all, there is a loss function global, which means that it is a loss function spanning the whole image, I would imagine, but we'll see more about it. Then it says forces unique predictions via bipartite graphs matching. So, but what are bipartite graphs? What is bipartite? See, in graphs, suppose you have a graph like this. Every node is connected to every node, right? This is not a bipartite graph. An example of a bipartite graph would be, suppose you have, for example, people. Right? So you have Ganges here, right? And let's say you have Prasanna here, and so forth. Are we right? Prasanna here. And here is your favorite food. Ganges?
Idli.
Idli. Prasanna?
Dosa.
Dosa. And Krishnan?
You already choose the.
So then that's it. You are allowed to choose the same. Idli, dosa, anything else?
Pongal.
Pongal.
No talking in bias.
There is no Indian bias. That's right. Vasanti.
Chapati.
Chapati. I find that a bit hard to believe, isn't it?
That combination.
Right. Right. And anything else? Dosa, idli, pongal,
Biryani.
biryani.
Karela.
Oh yeah, nice. Go ahead. And anybody else's favorite is biryani?
Yeah, but except
Such
that
it.
the person was.
Karela.
So guys, what do you notice about this graph that's different from the previous graph? What you notice is that there are two essential pillars or sets of nodes. The nodes are two different sets, and an edge goes only from a member of people set to a member of the food set, isn't it? So, for example, if this is the people, in more set theoretic notation, this is food, right? What it says is there are no cannibals here. People are not eating people, but all the lines are going like this. Isn't it, guys? That's it. In other words, nodes from this can be connected to one or more nodes in the other set. From the left set can be connected to one or more. These kinds of graphs are called bipartite. Bi means two sets, connectors between these two sets. Yeah. The graph is just made up of edges connecting members of one set to members of the other set. Yeah. That's it. They could be 1:1, many to one, one to many, many to many. Right? But it's bipartite. So now, we now try to look back via a bipartite matching. So that part we got. That forces laws, global laws that forces unique predictions. That part is a bit cryptic and it will make sense to you as I explain to you the paper, but we'll hold off on that. Right? I'll give you a flavor of it. All it means is that don't keep saying, suppose you have a picture and it has a cow and it has a horse and it has a bird, right? Don't zero on to just the cow, right? And keep saying cow, 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 and ignore the horse and the bird. Right? In other words, don't just pick one element and just keep pointing to this. Now, why in the world would you do that? It turns out that it has to do with the mechanics of this algorithm. Now, the next statement says, given a fixed small set of learned object queries, and that itself is again, so you can see that this person, like, there's a style which is meant for research, writing style, and there's a style that is meant to be expository or didactic or explain, pedagogical. This style is certainly not pedagogical because they're using terms before they explain what it means. But then it's the abstract, and people write abstract after writing the paper, and then they write the title. Right? So by the time they write the abstract, they forget that everything that they talked about in the paper is something that they just cooked up. Right? But that's how it is. People read the papers iteratively. So this abstract turns out to be very well written because it captures the gist of everything said, but we don't know what in the world this word means. Learned object queries. So I'll just park it as a word. Learned object queries are do you guys remember that I talked about blip 2? Do you remember some queries, learned queries there? That is what was triggering the one of the pillars, the third pillar.
Right.
Exactly the same. So these are learned vectors. So now we know in the architecture somewhere will be learned vectors in a way somewhat reminiscent of blip 2 came much later, but yeah, this is along the same spirit. Right? So this is that. Now, and what it says is that DETR reasons about the relationship of the objects and the global image context to directly output the final set of predictions in parallel. That sentence is the most important result, and that is the contribution of this paper. DETR reasons about the relationship of the objects and the global image context to output the final set of predictions in parallel. The new model is conceptually simple and does not require a special library. It's conceptually simple. Well, we'll see about that. And does not require a special library, unlike many other modern detectors. The DETR demonstrates accuracy, and which goes again to the fact that it's an end-to-end model. It doesn't just say, let this thing do this and then we'll do it. Go ahead. You have a question? No. So the new model is conceptually simple and does not demonstrate accuracy and runtime performance on par with the well-established and highly optimized faster RCNN. Now, remember, guys, last week we talked about RCNN, fast RCNN, and the faster RCNN. Or am I hallucinating?
No, the temperature is not.
My temperature is more. All right, I'll take that. Actually, now I realize I didn't talk to you guys. I talked to the advanced team, advanced LLM. Okay, these are the oldest methods, right? So first there was the RCNN, which basically said, okay, I'll give you the idea of the RCNN. What RCNN does, and remember, this was the time way before transformers came about. It was 2014, AlexNet had just come out, right? 2012, everybody was impressed. ResNet was was also there right at that time. And actually this paper came a few years later, but at that time, what it said is that let's use a CNN to create feature maps and then use a set of techniques to just suggest which regions are of interest. Right? Those were called proposed regions in the picture. And once you propose a region in the picture, then you just need a decoder to just tell what is in this region, isn't it? Object detection. What is in the region? Is it a cat? Is it a mouse? Is it a dog? Is it a tractor? Whatever it is. And the decoder, of course, was done with recurrence, and the encoding, the region finding the regions of interest was done with convs. That was the RCNN, and it went through faster. Then came the fast RCNN, and then came the faster RCNN. Right? A few variants of that, and that was considered the state of the art. But this paper moves beyond that and says, COCO, by the way, is an object detection benchmark. It's a data set you can use to check how well you do. Moreover, data can be easily generalized to produce panoptic segmentation in a unified manner. This masks, this colored things. Right? We just saw panoptic segmentation with SAM segment anything model, everything model. Right? We show that it significantly outperforms competitive baselines. Right? And again, the code is there on Facebook. So what does it do? Let's understand the picture from this main picture. And this figure, the caption says, DETR directly predicts in parallel the final set of detections by combining a common CNN with a transformer architecture. So guys, do you notice that it uses a CNN and a transformer? So think about it this way. Without reading the rest of it, what do you think the CNN will produce from the image? It will produce a higher order representation, a feature map. Somehow, we need to decode the feature map into, here is the bounding box. And by the way, this is about bounding boxes. Here is the bounding box and what is inside that box. Here is the rectangle and what's inside the rectangle, isn't it? So, for example, it may produce this pair, this rectangle and bird, right? Bird. It may produce this other rectangle and this cow as an example, right? Does that make sense, guys? It can predict, it can produce these pairs. And that's sort of the thing, in a way, later on we'll realize it's a bit restrictive. What it does is, you have to specify how many such pairs it will produce. Let's say n pairs. Pick n, 10, 20. It will always produce 10 pairs. Now the thing is, there may not be 10 birds or cows or ducks in the picture. Then what will it do? Then it will produce someplace. It will say, hey, that box, it has nothing in it. Nothing of interest in it. Are we together? And that other box has nothing of interest in it. It's sort of there in the paper. I'm mentioning it to you so that you have an idea of what's going on.
So this is from the transformer encoder decoder box.
Yeah, transformer. From the transformer will decode. At the end of it, what happens is that the transformer needs to predict or produce something, n objects.
So the input is only the images.
Only the image. Yeah. Now the question is, okay, this is good. Let's think now. And that is why when you look at this image, do you notice that the pink bounding box and the yellow bounding box make sense? They are around the birds. But what in the world is going on with that green bounding box?
No object.
Right? Well, suppose you have to produce 3 as an illustration. Then it is saying, hey, there's nothing there. Isn't it? By water being nothing. Unless you're thirsty. So there we go. So this will be this is the broad picture. So guys, let us iteratively understand it, because this is actually a complex paper. It's not that easy to understand. This produces a feature map. That's what CNNs produce, right? Feature maps. You feed that into a full encoder-decoder architecture, and then we'll sort of unpack the encoder-decoder, right? Because hidden in there are also this learned query vectors. Right? We'll come to that, but it is there. The important thing to know is it's a full transformer. What it produces is a set of box predictions. Means it will produce here 6 boxes and what is in the box. So when it produces, so think about it, guys, when a machine produces 6 boxes, in some sense, it's a regression problem because you're pointing out the location of the box. Bounding boxes are locations, right? Numbers. And what is inside the box is one of the finite set of objects that you may have, 50,000 objects that you may have, for example. It's a classification problem. And that has been the heart of segmentation in object detection, that it is a dual problem, both of regression and classification. Which is why people, if you look at the older approaches, they always treated it as 2-stage process. First, solve the regression. What are the regions of interest? What are the bounding box? And then secondarily answer the question, okay, now what exactly is in this bounding box? You see that, right? Now, this machine also claims, this paper also claims that this architecture does it in parallel. Namely, it will shoot out all the 6 bounding boxes in parallel. Are we together? It will shoot out all the boxes in parallel and tell you what is in there, which is a reference, I suppose, to the older way. Like if you are doing it with RCNN, recurrent networks are by definition sequential, right? So you know, a lot of the wording that people use has to be contextualized with the history that is there. So now, we compare to our previous work, blah, 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 we'll ignore all of that. Related work basically says ignore that. Now, let's go to set prediction. The set prediction is important. There is no canonical deep learning model to directly predict sets. This is a fact. What do machine learning models do? They predict either a class, probability of something, or they produce a number, regression. But you don't have a canonical. What does the word canonical mean?
Standardized.
Canonical comes from the word canon. Canon is a set of standardization rules. So there is no standardized deep learning model to directly predict sets. We don't have the basic set prediction task is multi-label classification. Okay? It is this and this and this and so forth. Right? So classification. There are lots of references for which the baseline approach, one versus rest, does not apply to problems such as detection where there is an underlying structure within elements, etc., etc. The first difficulty, blah, 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 blah. So let us just assume that they're pointing out that it's a little tough. Yeah. But the important word that I want you to focus on is, oh, Hungary has made its way in. There's an algorithm called the Hungarian algorithm. What is that? We'll come to it in a minute. This I'll explain. This needs explanation. A general approach to use autoregressive sequence models such as recurrent neural networks, in all cases, the loss function should be invariant to a permutation of the predictions. What it means is that, see, suppose I predict a set, right? I say this bounding box, cow, right? Bounding box A, cow. Bounding box B, horse. Bounding box C, bird. Now you realize that the order does not matter. The order in which I produce this elements should not matter, isn't it? It is the same information. That's what they are saying, that to do that, you need to have a loss function based on a Hungarian algorithm. We'll come to that. The loss should be invariant to the permutation of the predictions. How is it done? We'll come to that. And a bipartite matching. We'll come to that. This enforces permutation invariance. So that's the contribution of the Hungarian. And guarantees that each target element has a unique match. We follow bipartite matching loss approach. So this is what they do. So this is what they do. Now, transformers and parallel decoding. Transformers were introduced by Vaswani et al. As a new attention Are we all familiar with that? Yes, we are, right? Attention mechanisms and neural networks layers that aggregate information, blah, blah, blah. One of the main advantages of attention is their global computation and perfect memory, which makes them more suitable than RNNs and non-sequences. Well, some of the wording we wouldn't use today, but it is what it is. When they mean global computation, what do they mean? If you give it a sentence, they compute all each token in the sentence does self-attention on other tokens of the sentence in parallel. So it's a global computation in the sense that the whole sentence passes through in parallel through the transformer. That's what they mean by global. Make sense? That's right. Transformers are now replacing RNNs in many problems in natural language processing, and computer vision. So it speaks to the history of it. Transformers are first used in autoregressive models following early sequence to sequence. However, a prohibitive inference cost led to the development of parallel sequence generation in the domain of audio, machine translation, word representation learning, and more recently, speech recognition. So it just, again, speaks to the history of it. We also combine transformers in parallel decoding for their suitable trade-off between compute cost and the ability to perform the global computation. Now let's come to the main thing. 2.3. Object detection. The most modern object detection make predictions related to some initial guesses. Two-stage detectors predict box set with respect to proposals, right? Given bounding boxes, whereas single-stage methods with predictions with respect to anchors, like certain anchor points, or a grid of possible object centers. Why don't we skip all of that? Let's go straight to, forget prior work, let's go to the model. Two ingredients are essential for direct set prediction in detection. A set prediction loss that forces unique matching between predicted and ground truth boxes. Let me interpret this for you. Suppose there's a cow, a horse, and a bird there. What you want to make sure is one box points to horse and the other bounding box doesn't also point to the horse. It points to the cow and the third bounding box points to the bird. That's what they mean. Right? Is it there or he? I think it's there. There are many that predict a set of objects and model their relation. We describe our architecture in the figure that I believe encountered already. Now this is figure 1. So this is a figure 2 we'll come to in a moment. But before we come to that, let me do the main part. Actually, the main part of the paper is right this page itself. Here, what they say, DETR infers a fixed set of n predictions. Remember, I said that it detects n pairs. What is each pair made up of? A box, I, and a class I. Something. Bird, right? J. And all of these add up to n. So it means no matter what happens if I have more than n objects? Definitely. No. It will only spot n, of course. So that's one of the limitations. But actually, it's not a limitation because you keep n pretty big.
Is it not found?
No. Suppose there are 12 people and I give you n is 10. Then what happens? In an image, I allow you to spot only 10 bounding boxes. And there are 12 people. Then what happens? Yeah, so anyway, just be aware that there are considerations like this. Huh? Now, and they say that in a DETR infers a fixed set of n predictions in a single pass-through decoder where n is said to be significantly larger than the typical number of objects in an image. So in a typical photograph, let's say a family photograph, you'll have what, up to 50 people? Right? Good luck if you bring in an army of 1 million. So, one of the main difficulties of training is to score predicted objects, class, position, size, with respect to the ground truth. A loss produces an optimal bipartite matching between predicted and ground truth, then optimize the object-specific boundary map. So how is it? So everything seems to be, he keeps talking about a loss function, a magical loss function, that somehow can tell you uniquely, attach one box to one object, not repeat, and get it right, isn't it? So we better pay attention to what is that magical loss function. Let us denote by the ground truth set of objects. So suppose they are ground. We always use y for ground truth, and y hat is for predictions. Standard convention. Assume n is larger than the number of objects in the image. So suppose I say find 50 objects. There are 2 birds. Then what will happen? It will find other 48 bounding boxes will be what?
No objects.
No objects. Yes, exactly. We consider y also as a set of size n padded with no object. So in the training data also, what you will do, so suppose you have, look at the training data, you have 1 horse. Well, let me now reframe it as an elephant. Right? So this is it. So 1 elephant, and you are supposed to find 50. What will it do? It will go and say, okay, 1 elephant here, nothing 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 here, nothing, so forth. That is easy, right? But nonetheless, the training data associated with it, the ground truth, will therefore be a set of still 50 rows, 50 points, right? A set of 50 boxes and their identifications. That is the point they're making. Right?
Question.
Yes.
So usually elephants travel in herds, so you see only parts of the elephant and still be able to.
It's pretty good actually. That is one of the remarkable things you start observing when you bring transformers into the room. Even humans are able to do that, but a little bit more sophisticated. We'll get there. Go.
The object detection image has 2 problems, right? The where portion and what portion.
The where and the what, yes.
And in unit,
No, not just where and what, but how big, because the size of the rectangle.
Right.
See, if you can say that the top left-hand corner sort of addresses the where, the bottom right-hand corner addresses the how big in a rectangle. And then the question is, okay, what's in there?
So in unit, I think they solved it by the encoder steps was saved and the decoder used that for to recalculate the data. How is it done here? Because
we're going to learn that. We are going to. Remember, we just started this. So that is the big mystery. So this paper is actually one of the harder papers that we are reading in this course. So we have to pay attention a little bit. That's why I'm trying to go so slowly and break it down into pieces. Because it is like, generally, I've seen people struggle with this paper a little bit. Now it says, to find a bipartite matching between 2 sets, we search for a permutation of elements, sigma, with the lowest cost. Now, what it is saying is, let me take 2 things. There is an elephant and there is a little bird sitting here. All right. Let's take these 2 things. I can have the ground truth can be y ground truth can be this. Let us say that I have, okay, this, what just happened? I lost my ability to write. Okay. I will stop one note and bring it back. Let's see now. I will have to literally kill it. I apologize for these technical difficulties. Okay, let's try a look. What's this? Maybe the pen? Try another pen. Huh. Okay, guys, I'm having a bit of technical difficulty with this. With Windows, when all else fails, reboot. So please bear with me. I'm going to make one of you the host for now. Okay. And then I'll come back. I'll reboot this and come back. I don't know why this is happening. I'll give it one more try. But I've seen this happen in rebooting games. So here's the reboot. Okay, now comes the big question. Can I write on it? Yes. Rebooting solves all problems. All right, guys, I apologize for the technical difficulties, and I'll get rid of this Teams thing. It will take a minute. All right, guys. So here's the thing. Let's say that you're supposed to find 4 boxes. Right? Now, the 4 boxes could be, the ground truth boxes could be this, it could be this, and it could be, let's take another color. It could be 4 boxes. Right? Their locations are there. At the same time, they need to have in the first box, let's say ground truth is the, oh, no, this is huge. Elephant. And the second box has the word bird. And the third box has the word nothing. And the fourth box has the word nothing. Are we together? This is the ground truth. Now, think about it. If you're going to predict 4 pairs of boxes, you predict a blue box. I mean, let's just say 4 boxes, and I'll deliberately use a black color because we don't know which box is which. 4 boxes. So One part is that the boxes should be in the right place. Would you agree? That is one part of your loss function. Yeah. Right? That is common sense. The other thing is obviously a loss associated with the boxes should overlap. They should match. One shouldn't be bigger than the other and so on and so forth. So this is it. Oh, what did I just do? This is this. Let me turn up the touch. Okay. Did I turn up the touch? Touch up. Okay. So this is this. Let's read through it very carefully. And this part, guys, does it look like your normal? What is this term?
Negative loss.
Negative loss. Right? If it is supposed to be a cow there or an elephant there, what is the probability that you are giving to an elephant in that? That part of the loss is understandable, isn't it? That's your negative log likelihood. Now, let's read this more carefully. So you pretty much are getting the main thing. You're saying we search for a permutation of n elements with the lowest cost. So for example, if I got the box location right, but I put nothing into it, is that a good idea? No, right? So this is it. You look for that combination which gets everything right, where matches is a pairwise matching cost. Now, here is something interesting about it, that this paper matches. See, when will I have the lowest cost? If I have already put an elephant here, let's say that I got the elephant right? Now, should I go and put the elephant here also? Make another bounding box? Like, what happens if I hypothetically just say, I make this bounding box blue, put an elephant there, that's right. But suppose I make the mistake, the machine makes the mistake of making yet another bounding box at exactly the same location, right? And says elephant. Just look at the hypothetical situation. What will happen?
Elephant or some other?
No, elephant itself. It keeps on saying elephant, elephant, elephant. Like kids do that sometimes. Right? They find something very interesting. They say, look. So suppose you do that. Then what will happen? You realize that, and let us say that the worst case situation, all of those false bounding boxes are pointing to the same thing. Do you realize that these losses will blow up? These losses will completely blow up. Isn't it? Neither the location nor the class will be right. Am I making sense, guys? And so, if you use a loss function that looks for this sort of a match, right? It will force that if you have found an elephant, you don't put another bounding box around the same element, isn't it? You don't make bounding boxes one on top of the other and call it elephant. Do you see that? No. It will, because other loss terms will begin to blow up. That is the Hungarian loss that he's talking about. So what it says is that where loss is a pairwise matching cost between ground truth and a prediction with the index I, like index means first, second, third, fourth item, this optimal assignment is computed efficiently with the Hungarian algorithm. There's an algorithm to do that. The matching cost takes into account both the class prediction and the similarity of prediction and ground truth boxes. Class prediction is your negative log likelihood, and the similarity of predicted and ground truth boxes. This is it, the similarity, right? Each element of can be seen as this is a vector. Each bounding box is a vector that defines ground truth box center coordinates and its height and width relative to the image size. For predictions with blah, we define probability of the class as blah, which is normal. With this notation, we define. So this term is very standard. Okay. Right. Now, for example, guys, how do you know that two boxes are completely matched? Geometrically, what is the degree of match? Like loss would be the mismatch, isn't it? So what would be the intersection what would be the difference between the intersection and the union?
0, I think.
If two batches are completely matched, will the intersection be 0?
Equal to union.
Yeah, intersection will be perfect.
Yeah, I
The
mean,
A intersection B will just be A.
yeah.
A union B will also be A.
Yeah.
Isn't it? So intersection over union, if I divide intersection by union, that ratio is a good example of how much match you have, right? When two boxes are completely separated, what would the intersection be? 0. When they're completely overlapping, the intersection would be like completely 1. Let's say that unit box. But in any case, if you divide it by the union, you see that the ratio is a good measure of the degree of mismatch between two boxes, isn't it? Right? Or taking the log of it and so forth. I mean, you can do operations on it. But the bottom line is that intersection over union is one. I don't know where it talks about it, but I hope it does somewhere. But anyway, we leave it there. And so you can create a loss function, basically saying, are my bounding boxes correct? Are they the right bounding boxes? Blah, blah, blah. Right? I won't go over that. Yeah, IOU. Oh, lovely. IOUs. IOU loss. Intersection over union loss. Right? It may not have explained. So anyway, this is it. DETR architecture. So now let's come to the architecture. How does it do it? First thing, guys, when you have a CNN, will extract the features. So you see the features getting extracted. Now, for the feature, given the feature map, you also need to give the position encoding of where the objects are, right? Somehow, right? You give the position encoding, feed it to a transformer. What happens to the transformer? What does the transformer encoder take? Remember your basic architecture. Word embeddings plus position embeddings. So that is it. In this particular case, actually, what they did is they just unrolled the CNN. They literally unrolled it into flattened it out. All the feature map, row by row, scanned it and flattened it out. Like, what is it called? Squeeze, for example, in PyTorch, squeeze the matrix to make it linear. Yeah. Then add position embedding, shoot it up. Now you got all your feature maps and you got all those things. They are like tokens. You pass it up. Encoder will produce you a hidden state, a latent state, which goes into the decoder. But there's a problem. You're not doing a causal model. So you can't, there is no one token generation followed by next token generation in the decoder. So what do you need to do? You need to trigger it with something here, right? At the bottom. You need some vectors to feed in. Where do you get the vectors from? You say, oh, well, let backpropagation learn it. Right? We'll just feed it some random vectors and then let the machine learn it. So this is the object queries. These are the learned object queries. Let me put it this way. Learned, or nowadays people don't use the word T, learned object queries. Learned object queries. And they trigger it, and then the information is coming from the encoder. Your normal decoder thing happens. And what happens? Decoder is producing what? It's going through the feed forward network, blah, blah, blah. But it is producing ultimately the boxes and the classes. Class box pairs. Right? Well, I wrote box and class. So the convention. So you notice that I tend to write box and class. But here, the reverse. Okay, it doesn't matter. It doesn't matter. It's the same thing. And so you come up with this.
So how do we come up with those object queries? Like,
oh, that's what I'm saying. When you're training the machine, just randomize it. And then through backpropagation over thousands of that, it will learn what are good query vectors. Now, what is the intuition behind those learned query vectors? Learned object queries, right? What are the intuition? See, what they do is, when you, and I don't know if it is talked about in this paper or not, but certainly the author talks about it somewhere in one of the encoding attention, the encoder is able to separate. Okay, let me see if he mentions it somewhere. They mention it somewhere. Oh, yeah, sort of visualizing all the box predictions on all the images. Each box prediction is represented as a point to the coordinate, normalized, The points are colored. We observe that each dot specializes in certain region. Box predictions. We observe that each dot learns to specialize in certain area and box size with several operation modes. Okay, so basically what it means is that, see, all of these learned queries, right, they probe different parts of the image. One will say, what's there in the bottom right? Yeah. One will say, what's up there? One will say, what is up there? And when you look at it, what happens is these queries, they're actually fairly spread out and they're probing different parts of the image and asking, what's here? What's here? What's here? What's here? That makes logical sense, right? It sort of spreads out and asks you, what is in all these locations? Yeah. And there may be nothing or there may be something. So
the training data set, so somebody has to do this, like the boxes, the bounding boxes. Right?
Yes, yes. Training. So yeah, very good question, Ganges asked. How do you train these machines? What you do is you take a lot of images, which is fun. Then you go out with the camera and shoot. And then comes the part.
That is not fun.
That is not fun. You go, every time you see an elephant, you say, instead of saying, oh, cute elephant, now you sit down and start annotating the data. You say, okay, elephant. And you create a lot of annotated data. And this is how labeled data is produced. That's why supervised learning is so hard.
I think in the labeled data, learning elephant is like a feature you can learn. But what is no object? No object is anything.
Yeah. So what happens is, suppose you set n is equal to, let's say, 5. And in the picture, there is just one elephant. What you do is, in a post-processing step, either you can label it, just randomly pick 5 points and have a, say, no object, no object, no object.
No, in the training, the training, what is the machine learn? If I give you computer, fact, all of that is no object. How will the features kind of learn? How is it learnable?
How does it know that you have to ignore the cup?
Yeah.
How to ignore it? Oh, it literally learns from that. See, if you give it enough training data and everywhere the cup, it notices a cup, but it is being taught that, hey, don't call it cup. Yeah, that is it. And in fact, that's why you need such a huge data set. And labeling is important. So what happens is, see, for example, water, a lake. Should you really ignore a lake? Lake may be the feature you're looking for in a topographic image, right? And that's where, the models are highly dependent on the biases that are embedded in the data set itself. So anyway, guys, so that's that. And I'm on the hour. I will take 1 more hour, guys, or not. It's 5 o'clock. Okay, guys, here's the thing. I won't take 1 more hour, but let me just see. Do you notice how encoder self-attention for a set of reference points? Do you see that the encoder, what is it producing? Encoders produce attention maps, right? In some sense. Do you notice how well it is producing attention, self-attention? Just looking at this attention heat maps, would you agree that it knows where to pay attention to in the picture? Right?
It's similar to the masks that we produce.
It's like so it will lead to, it's practically the answer. You're right. In a fully trained network, encoder practically has figured it out. It at least knows the regions. Now you just have to figure out what's in the region, right? And how big the bounding box is and so forth. And it's quite beautiful, actually. Do you see how it is able to separate the things out, right? And there's more to this paper. I won't go too much into it. But see, this kind of an image, you would agree, is a little bit hard. 2 overlapping elephants in the picture, isn't it? Or look at this zebra. It's not so easy to get it right. And yet it seems to get it right. Yeah. The performance, obviously, if you notice, it matches the state of the art. I won't go more into that. See, the main point of this, and this is the panoptic, so this is the masking. Do you notice how well it does the masking of objects? Right? Yeah.
Is it as lightweight as CMS?
Oh, no. Transformers, the word transformer and the word lightweight are poles apart. Yeah.
Can this do image capturing better than if you use this architecture because it can detect every object?
See, there's a subtle difference between image captioning and object detection.
Right.
Just because you detected the object, you have solved only half the problem. Captioning is more than that.
You feed the text.
You can feed it. This is exactly how lava works. One of the things is,
Right.
what does it do? You take in the first stage is object detection, the bounding boxes and the things. And then the second stage is it puts an interpretation on top of it and writes a caption. So that's what it is. It's half the journey. Go ahead.
I'm assuming, like, going back to the Tesla example, where Tesla is using something like this to detect people and objects.
Yes. I mean, segmentation is at the heart of. I mean, it's the eyes. One of the primary visual tasks in an autonomous vehicle or any of these things, robotic structures that are moving around on factory floors, is image segmentation and object detection.
So what I've seen recently is that in the Tesla camera, when there is one person, it shows 5 people. I literally saw that a couple of days back.
Oh.
Instead of one person next to the car, it
Yeah.
shows the image of 5 people.
Oh.
Of people. Sometimes a group of people with a small bicycle is what I saw, but there is no bicycle. So I'm just wondering what the model is doing there.
I think the model has started smoking pot.
Being extra cautious.
I don't know. Now, so those are bugs, actually. The problem is, anyway, I'll make this comment after the